Hello everyone, my name is Bora Ulaş Bakandı and I'm the leader of Group 4. We're going to be doing our presentation on our exploratory data analysis of our data set today. My team members are Doğan, Berkay, Sözer, Mahmut, Furkan, Bakal, and Zeynep, Nedret, Ulaş. As an introduction, we want to discuss things like why we chose this data set, the source of our data, and the samples and features of this data set. This is the source of our data. We found it through Kaggle, and as you can see, it's a data set made specifically for wall-following robot navigation. So this data set aims to help wall-following robots help navigate rooms and environments through ultrasonic distance readings and the directions it should turn according to those readings. We'll get into those details in a second, but for our case, we wanted to make an algorithm that helps a robot navigate in a clockwise direction around a room or other enclosed environment. So why did we choose this data set? Well, primarily, we chose it because it was the most usable and most workable out of all the data sets that we looked at. Through the recommendation of our instructor, we decided that the features and samples and the overall format of the data set was easier for us to work on compared to other data sets, and also because it was something we could all find some interest in terms of subject matter. Now, the benefits of using machine learning algorithm for this case is that most of these wall-following robots either have to be pre-programmed or have a pre-planned path that engineers and programmers have to program beforehand, which is not ideal for robots that might be placed in many different kinds of environments and may encounter unexpected situations, especially if these robots are going to be consumer products that need to work in all sorts of homes and all kinds of rooms. One could also program the robot to scan its environment before trying to navigate it, but this is of course slow and possibly inaccurate if done from a single reference point. The aim with a machine learning algorithm is that navigation could possibly be done in real time and as the robot is navigating. So there's no need for pre-programming or for the robot to scan its environment, since it can adapt to the situation in real time. As for the samples and features of this dataset, the dataset itself contains 5,456 samples with 25 columns. 24 are numeric features, and 1 is a categorical outcome with 4 classes. We'll discuss these samples and features shortly. So in this dataset, we have 24 columns that refer to these ultrasonic sensors and their distance readings. The sensors are labeled V1 to V24. With the help of these sensor readings, we can help the robot navigate an environment without colliding with any obstacles or obstructions. Of course, these numbers in these columns refer to the sensor distance readings in centimeters. The final column in our data set is a class type variable. This is categorized from 1 to 4 and determines the direction the robot should turn. Since this robot navigates the room in a clockwise direction, sharp left or move backwards were not included in the dataset because they're simply not necessary for this application. If it did navigate a more complex environment with a more complex path, such as a maze, these classifications would be necessary. But since we're primarily dealing with one direction of turn, we simply do not need to take these other directions into account. This simplifies our task and makes it more specific to wall-following robots. The machine learning algorithm that comes from this is also going to be specific to the range of classifications provided by the dataset, such as the tolerance for collision distance, speed of the robot, turn rate of the robot, etc. As long as the data provided by the robot itself is reliable, so should the resulting machine learning algorithm that will inherit the navigational characteristics of the original robot. This is, of course, a supervised learning task since the intended classifications are provided in each sample. And the classifications of these 4 classes are 1 to 4, and they are move forward, which is no turn, slight right turn, sharp right turn, and slight left turn. These are the locations of our sensors. As you can see, there are 24 sensors in a circular pattern around the robot, so 15 degrees of separation between each sensor. For reference, 180 degrees is the front, negative 90 degrees is the left, 0 degrees is the rear, and negative 90 is the right. This is the reference that we used to refer to the sensors and their direction in our analysis. Finally, this is the robot that was actually used to take measurements and collect data for the set in real life. This is a photo of the robot in action. Next, Berkay will continue with the feature selection of our data set.
Hello everyone, I am Doğan Berkay and I'm going to talk about the sample features. But before moving on the feature selection, I want to mention that what is our robot looks like and where we should place the sensors. And as you can see, this is our sample robot. The dataset includes information on the use of 24 sensors located around robots, which are used to detect objects and obstacles in its environment. When an object is detected by any of 24 sensors, the robot collects the values from the 9 closest neighbors to obtain a more precise understanding of the object's position and shape. And this approach is particularly useful in helping navigate the complex environments with varying obstacles and shapes, where it's essential to have the accurate information about the objects in the environment, avoid the collision, and maintain the safe navigation. We can move to the next slides. Firstly, we decided to choose V4 and V22 sensors to describe it, because these are the front two sensors, which is on the right. V4 is on the left side and V22 is on the right side. Comparing these two sensors, we can see that they provide information about the robot's proximity on the wall opposite sides. While V4 measures distance between robot and the wall on its left, V22 measures distance between the wall and the sensor on the right side. And in terms of their relevance for the wall-following robot navigation system, both are the important features. However, the relationship between V4 and V22 can vary depending on the strategy. When the V4 value increases, the V22 value may either remain unchanged or decrease. By the meaning of the value increases, we are examining the values in centimeter to the wall and the sensor. And this is because an increase the distance between the robot and the wall on the left side. And we can move the next slides. Secondly, we decided to choose V7 and V19. This is because these are the sensors are the opposite sides. While V7 measures the angle between the robots oriented on the wall left side, V19 measures the robot on the right-hand side. These are the, again, important features. And when robot if there's an example that I have to give you, when robot follows a parallel wall, the difference between the angles measured by V7 and V19 should be small, indicating that the robot is aligned with the wall. On the other hand, when the robot encounters a corner or a curved wall, the difference between the angles may be larger, indicating that the robot needs to adjust its oriented. Therefore, the values V7 and V19 are interdependent, and analyzing them together can provide a better understanding of the robot situation. And we can move to another sensor. And these are the opposite side of the sensors, that's V3 and V15. We can say that these are the sensors that opposite sides. Because of that, the relevance of the following navigation, both V3 and V15 are important, and they avoid the collision. And their relationship between them is not exactly the same as the before examples, because they are the opposite sides. When V3's relevance is going up, our V15 values goes down, and the opposite side, when the V15 values goes higher, and the V3 values goes lower than that. And we can move to our last selected sets. We choose the lastly two closer sensors than the others. Since these two sensors are closer to each other, we get this plot by using defined informative projections property. And the relationship between these two sensors are dependent to each other. If one of them increases, the other one should increase too. Since these two sensors are much closer than the others that I mentioned before, and because of these are more closer together, these plots are much nested. And we can say that simply by looking at the variables. If V18 goes smaller, V15 goes smaller at this time. and we can move on. After examining these datasets, we can say that conducting a true review of the scatter plots and closely examining the distribution patterns within our dataset, we came to the realization that our dataset was exhibiting a significant level of imbalance. Specifically, we found that the certain classes within our dataset were significantly underrepresented, while others were overrepresented, creating a potential for bias and inaccurate predictions. Furkan will deeper into the specific details of our approach, highlighting the key points and involve the relation behind our decisions. And now Furkan will continue. Thank you.
Hello everyone, my name is Furkan from the Software Engineering Department. And now, as my friend Berkay said, our data is imbalanced state. And the question is, what's the imbalanced dataset and how we handle this imbalanced dataset. And class imbalance is when the number of samples from different classes in the dataset differs greatly. In our datasets, the third and fourth class have less sample than the first and second class. In this case, machine learning models may perform better against more instantiated classes, but poorly against less instantiated classes. As a result of our research, we found two solutions, oversampling and undersampling. And the undersampling method tries to equalize the number of different classes in the dataset by subtracting some of the samples from the more instantiated classes. And the oversampling method tries to equalize the number of different classes in the dataset by copying samples from less sampled classes. In our dataset, we decided to use oversampling in our dataset because we already have few samples in our dataset. And if we remove some of the samples in some classes by applying undersampling, we will not have enough samples after this undersampling operation. And we use SMOT oversampling technique, which is synthetic minority oversampling technique. And how it's work? As you can see on the graph, the circles is represent majority class samples, and the plus is represent minority class samples. In the SMOT, we select randomly a minority class sample, and after that, we found his KNN neighbors of this sample. And after that, we again randomly select a sample from these neighbors. And finally, we generate a synthetic minority instance between these minority class and neighbor minority class samples. And we couldn't find how can we do this on the orange tree, so we did it using Python. Next slide, please. And after this oversampling operation, our datasets became a highly balanced state. And now we have nearly 9K values. And next slide, please. And this is a new version of the scatter plot that Berkay showed before. And as you can see now, we have more samples from the third and fourth classes. And next slide, please. And in the guideline, you said if you have a sample number less than 10K, you need to handle this. We have nearly 9K value, but we did some research on how to overcome this problem, but we couldn't find any results for this problem. So we thought an idea ourselves. We wanted to ask if this idea makes sense or possible logical. To solve this problem, we thought of creating new class, sharp left turn. In our dataset, we don't have this class, and we thought of using the sharp right turn data for creating these new classes. We thought if we replace the sensor data created by our robot while making a sharp right turn with the sensor data in the opposite direction, like a mirror. And we think if we use this operation, we will obtain our new class sharp left turn data. Next slide, please. And if we use this adding operation after the class, now we have nearly 11K samples, and our dataset still balanced position. And next, please. And that's the final version of the scatter plot that Berkay showed before. And as you can see now, we have another class, which is represented yellow, the fifth class, which is sharp left turn. And next slide, please. And now you'll see the correlation between the feature, between our sensors. And the correlation you see here are related to position of sensors relative to each other. And as you can see, there is a high cohesion between the sensors that are next to each other or in the opposite directions. Because naturally, as you get closer to an object, the adjacent sensor increase together. And while for the opposite direction sensors, one increases and the other one decreases. Next slide, please. And these are less correlations. And again, it's related to position of the sensors position of the sensors to these values. And now Zeynep will continue.
Hi, I'm Zeynep from Computer Engineering, and I'm going to talk about the little details about our data set so that you don't have any question marks in your head. First, I'm going to talk about duplicated data. In our data set, our rows don't have any duplicate data, so it's a good thing as data from two different features cannot have the same values at the same instance. It would give an error. But on the other hand, other columns can have duplicate data, and our data set has that too. So that's fine. Next slide, please. About the missing data, our data set doesn't have any missing data, but we still use the input gadget on orange. As you can see on each screenshot, the bottom left side, there's an input number and an output number. All three don't have any missing values after this. After applying this, it removes instances with unknown values. Next slide, please. For future engineering purposes, we used one-hot encoding. This technique is one of the most popular techniques used for turning categorical values into numerical values, as some machine learning algorithms like k-nearest neighbor cannot interpret categorical values. They need numbers as they depend on mathematical equations. So one-hot encoding does that. As you can see, we have 5 classes now after the sharp left class addition. It's a binary. They are encoded in binary, so they all have unique encodings. This is just a feature engineering suggestion that we came up with, and that's all. Thank you.
Thank you for the presentation. I have several questions, if you like.
Yes, sir.
First thing that when you consider the values of the sensors, reading values, you compare the opposite side sensors and similar sensors, or located similar side of the robot. But you didn't mention that if you need to remove some of these sensors readings, because if they are very close to each other, most probably they are reading similar values. Have you noticed that?
Yes, but we decided that we shouldn't remove any of the sensors because of the positioning. Since our robot aims to move along the room, after that we are trying to move our robot in a room with carrying something, as Ulaş showed a picture of that. And since it carries something, that needs to calculate much more samples than 12 or 8 sensors. Because of the 24 sensors are needed, it goes to nearest nine sensors for the left side, for the right side, and it calculates every centimeter between these sensors. And according to that numbers, we can adjust our way to get out of this situation.
What about the other team members? Think about it. I'm suggesting you can, you may, you might reduce the number of the columns by selecting some features. This time the features are the readings from some sensors. You can simplify the input. Did you consider this? But actually you need to consider, right? And if there is a reasoning why you didn't do, explain this. But if you didn't consider this, tell me why not.
Yes, sir. What we thought is it's possible to reduce the number of sensors to, let's say, by half, by 1/3, by 1/4.
Well, I am not saying that by randomly. Depending on your problem domain, I am saying that they are only 15 degrees different from each other, right? So it might be a good idea because in some machine learning problems, decreasing the unnecessary number of features will help your model much. Did you consider this?
Yeah, so we thought that with more data, more sensors, we thought like the algorithm can have a higher fidelity in terms of having a better idea of its surroundings, such as differentiating concave and convex corners in a room and other things like that. This is like more data will be more helpful.
And also, I think if more sensors will be good for us if our obstacles are small. For example, we have two obstacles in between 15 degrees nearest. The more sensors, it will be good, I think.
Zeynep?
Honestly, I don't have an idea.
Okay.
I don't have anything to add.
Then let me ask another question. Since the sensors are very close to each other, 15 degrees separated, right? Did you consider to put some of them together to create new features? Like that, you can put 3 neighbor sensors, get them average, right? Their average, and create a new reading, new feature. Did you consider to increase the number of the features? If you think that these features are important, then I would think that if I were you, maybe I select 2, 3 nearest neighbors of the sensors and get average of them and create a new feature adding these 24 sensor readings as new reading. Did you consider this kind of feature engineering?
Actually, we think this kind of feature engineering, and we want to ask you this question after the presentation.
Now this is my time. I am asking the question.
We think that we can use this technique for increase our samples, but we didn't sure precisely. So we want to ask you too, but if you are asking to us, then we get our answer.
Okay. So in the exploratory data analysis, the feature engineering is also you need to think about it. Okay. And I have less than 10 minutes. So, okay, I will ask several questions quickly. You mentioned that your data is imbalanced, right?
Yes.
Yes. And on that slide, could you go to that imbalanced data set slide? You mentioned about 2 methods, which are very well known, right? Oversampling
and undersampling.
Undersampling.
Okay, please do not stop the slides, okay? Just go over back or next, okay? Or just click 10 and enter, okay? That's all. And I am asking, there is the first method, but you forgot it. What is the first most important method to your team members? If your data is imbalanced, what is the first thing actually you need to do? Not only oversampling, undersampling, smooth or something smooth, but there is actually one thing that you have to do always first. Any team members?
I don't have any idea, sorry.
V2,
No, Mahmut.
unfortunately.
Doğan,
I don't have any idea. Sorry.
Zeynep.
Jim, is it a machine learning method or like an algorithm or
No,
something else?
something else. Very simple.
I don't know that.
We can look for another dataset in the
Not
very
another
beginning.
data set, but
Similar dataset with the other features.
no,
maybe.
don't count,
Oh.
go further.
Okay.
What could be from the audience? What could be the first thing if your data set is imbalance? What can you do?
K-cross validation?
No,
No, okay, no.
not the first thing. Okay, I will tell you. Everybody knows actually. Collect more data. Right? In the real life, you need to collect more data, right? If your robot, if this robot belongs to you, you can collect more sharp right?
Yes.
So then your data set would be balanced. Don't forget, in real life, before applying this kind of methods onto your data set, please try to find better ways, the most good ways, the best ways to collect more data if possible.
Okay.
Okay. And then why did you use input? I didn't understand. There is no missing data, but Zeynep, you use input. Why?
Just to be sure that we don't have any missing data.
But in the data table, it is written that there is no missing data.
Yes. We just wanted to add it last minute.
So don't do this, okay?
Okay.
Unnecessary. And you talk about one-hot encoding in the next slide, Zeynep.
Yes.
Okay, which gadget in the orange do you use? Did you use?
It's not on orange.
Why not?
I don't know. Hocam, they don't put it on orange.
Hocam, ask the Orange developers.
No, there is the tool. I will teach you.
There is?
In the
Actually,
3 weeks later, I will teach you. So there is a tool. There is a gadget.
I couldn't find, and I searched on the internet and I couldn't find again, and so
it is
I
there.
have to use the Python.
There. From the audience, anybody knows encoding tool, one-hot encoding tool in the orange from the audience?
Maybe feature constructor.
Which one?
Feature constructor.
In the feature constructor gadget, did you use it?
No, actually I tried, but I cannot find one encoder too. But maybe feature constructor help us.
Okay, so I hope that in the next presentation you will explaining us how you use the one-hot encoder in the orange.
Yeah.
All right.
Okay.
Okay.
So overall,
teacher, is it
say again.
is it edit domain?
What? I cannot hear.
Is the tool edit domain?
No, but could be inside. It should be in 2 places. Okay. So thank you for the presentation. But please think about the feature engineering as well. And you need to check if what could happen, preliminary analysis. You know that the increasing, decreasing the features can affect the success of any machine learning model. So in next presentation, I suppose that you are gonna come back these exploratory data analysis and you will do some changes because you would understand your data better when you apply some machine learning models. So I would like to see this explanation in your final project as well. Please download the template project report, final report, and already fill in it with this information, okay?
Okay.
Thank you for the presentation. Any question from the audience? Any questions? Huh?
No, hocam.
Okay, thank you for the presentation.
Thank you.
Sir, thank you for listening.
Thank you, sir.